I go till 50. I go till 11 shift.
Yeah, even 55, usually there are wrong questions. But that's okay.
Yeah, that's perfect.
Okay, so we're very happy. Theja Maguluri is the House Family Legal Professor at the University of Systems Engineering. He obtained PhD at UIUC and BTech at IIT Madras. He works in several areas, control optimization algorithms by probability. In particular, reinforcement learning. Today we're talking about Markov chains. And his research and teaching have been several awards. These include the Best Publication Applied Probability Award, NSF Career Award, the second place award in Forms KFIB Best Paper Competition, and also Junior Faculty Teaching Excellence Award and Student Recognition of Excellence in Teaching Award. So with that,
I don't want to say Pranav just came. There's the student recognition of excellence in teaching. So there's a course survey at the end of each semester that the students fill out, right?
So it actually is not an award, it's a non-award. You should try.
It's a popularity contest, basically.
That is right, go. I want to organize it.
Thanks for the reminder. Okay, good morning, everyone. Thanks for having me here, especially at such a short notice. So I'm in Mumbai, mainly visiting IIT Bombay for a summer school. Last week, I was there. So I thought it would be nice to stop by here for a day. Should I stand here?
No, I mean, stand wherever you're comfortable.
Oh, okay.
yeah.
I know that.
So I thought I'd start with a quick overview of what I do. I call my core group. It stands for Control Optimization Algorithms and Randomness. And it's also, all of this is important, that's why it's core. And big chunk of my work is on stochastic processing networks, essentially queuing systems that, oh, this is messed up. Okay. I hope other slides are okay. Queuing systems that appear in a variety of systems such as cloud computing, wireless networks, and so on. And in this context, we developed drift method and transform method, which are analytical tools that one can use to characterize the behavior of various policies and use these tools to also develop new algorithms. A second line of my work is on online marketplaces and matching queues. So here the goal is to match a rider and a driver on a platform such as Uber. And even though it appears to be very similar to a traditional queue, it has what I call as matching or two-sided queue, because both drivers and riders arrive and depart, unlike a traditional queue. And then traditional queuing results cannot be directly applied. So in this domain, we kind of developed foundational theory for matching queues and then used it to study ride-hailing and electric vehicles. And the third stream of my work is on stochastic approximation and reinforcement learning. I spoke about this at the summer school, so I decided not to talk about it here. So many reinforcement learning algorithms can be thought of as instantiation of stochastic approximation. And then again, we developed over the last several years methods to get finite time bounds for stochastic approximation under fair amount of generality. And then these results immediately imply sample complexity results for reinforcement learning. So once you have a stochastic approximation finite time bound, you can almost plug and play to get sample complexity of various reinforcement learning algorithms. This is what I've been doing for the last several years. And then in the last couple of years, I've been trying to get into some new stuff, new to me, mostly on things like concentration, mixing, and stuff like that. And I thought today I'll talk about some of our work on mixing. So it broadly falls into this, but I'll not really talk about any applications. I'll mostly focus on a fairly abstract and simple queuing model, and then talk about mixing in that context. So I think the background is that Markov chain mixing is like a very old area, but there is a lot of resurgence in the last few years. Piyush has some awesome work. There's also a lot of developments, especially from the CS theory community. But a lot of this is focused on finite-state Markov chains, because that's what arises in CS, I guess. I thought we'll take a slightly different approach and focus on infinite-state Markov chains. In infinite, there are countable and uncountable. So there's also a lot of work on uncountable state Markov chains, especially those that arise in the context of SDEs and so on. And countable state Markov chains have a lot less literature in comparison. So my focus is going to be on countable state Markov chains, especially on queues. Good. So this is joint work with my current PhD student Huang Nguyen at Georgia Tech. Huang is now a fourth year PhD student. He was actually a silver medalist at International Math Olympiad, and last year he spent about 9 months interning at Google DeepMind, and he was involved in the system that Google built called Alpha Geometry 2, which competed in the Olympiad last year and then performed at silver medal level. And then I spoke to him just a while ago, and he told me that tomorrow is the International Math Olympiad in Australia, and then he has a part-time role with Google right now, and then they're working on seeing how this performs this year. I don't know anything about the system. I'm not involved in it, but Juan can talk about it. And this is Sushil, who is my former PhD student. He finished his PhD last year, and he's going to join Michigan as a faculty member in a month. And then he deferred that offer for a year and then spent a year as a postdoc in India, Paris. That's where he is now. Cool. Queuing systems arise in many applications. This is airport wait times. This is immigration, visa and green card applications. And this is data centers, delays in data centers and so on. And in many of these, one is interested in things like average wait time, or this is like a tail bound. 80% of the cases finish in 16 months. So this is like the 80th percentile delay. So usually we model these using queuing systems. And when we do that, sorry, I'll come back to this in a bit. When we model this using queuing systems, usually in practice, the kind of things we're interested are finite time behavior. I don't want to wait until steady state. I run the system for some time and then I want to understand its behavior. The reason we don't want to wait until steady state is these are time varying systems. The arrival rate has probably some seasonal or even during the day or during the week, there are fluctuations. So we want to understand things after just a finite amount of time. And then we are interested in things like mean delay and tail bounds, as I pointed out in the previous slide. But in theory, what we have is steady state behavior. And many a time in queuing theory, not even steady state behavior. We have steady state behavior in certain asymptotic regime as the number of servers goes to infinity, or the traffic, something called the heavy traffic limit. We'll talk about it in more detail as we go along. Because you can't get exact behavior even in steady state, one tries to get asymptotic characterization. So there's a big gap here. And the goal in this project is to develop queue-length bounds for finite n, finite load that is not heavy traffic, and finite time for queuing systems. I think the slides are messed up actually.
So some of PPTX, when you transfer it to a different Windows machine, I mean, like it may not work.
I see.
That's the transfer.
Yeah, the alignment is Nitin still here?
I mean, like, do you have a different? Do you want to use a different?
I have my laptop.
Yes. Okay, that might be the easiest.
So just start on your Windows Zoom.
Okay.
So you have the Zoom link.
I want to capture our technical video.
How does the speaker react to technical troubles?
We can get an award if you react for
You should have checked the slides before we started. So here, yeah, you can just disconnect audio. Just click on. Okay.
Or you pause the recording.
I think it's.
I didn't pause the recording. No. The disconnect the audio. This is currently muted.
Okay.
Leave computer audio.
No, it is recording.
Yeah. Oh, recording paused.
Yeah, that's good.
Oh, okay.
Share screen.
Yeah, you can just share screen, whichever screen.
They will not get any news like this. Come on. The whole point is to get views.
See one more drama.
Yeah.
Somebody will make a YouTube short.
Theorems have enough drama, you know.
We should do that. Try YouTube bloopers in STCS seminar.
Yeah. So there is other kind of video, right?
Short, yeah. Kind of only this part.
So, okay, cool. We are all set. I don't want my laptop to die.
You can continue. I'll just plug this in.
Okay, thanks.
You can unpause it.
Yeah, I'm well prepared. I have a clicker. Yeah, we are
Have the same clicker, by the way.
I know. Yeah, that's the clicker. Cool. So
A little bit of lag, is it?
looks like.
Is it?
Oh, okay.
Is it? And then there's lag.
Strange lag.
There is a lag. There is a lag.
So you're connected to which Wi-Fi?
Eduroom?
Okay.
Eduroom.
I'll just turn on my hotspot then and just be.
But you works faster than me.
No, our Eduroom is horrible.
But our TFR Wi-Fi works quite closely.
Yeah, but TFR Wi-Fi needs the whole bunch of.
Oh, okay.
Yeah.
No, but hotspot your officer can share from TFR.
Dude, now I am on YouTube, man. I mean,
He's also the CISMA, our representative.
I would just want to remind you, I'm on YouTube. Okay.
So this is the Netflix Shorts moment. 5K views.
So for those who don't know, after the involved.
You can see his network name.
I think that show that still.
Yeah.
This is not so big. But why did we part with that? So that's it.
I'm telling you, our subscriber count is about to skyrocket. We just need to publicize this. Put that in the publicity, so.
It's connected. Hopefully, it will now be okay. Should I just share this?
That's fine. Screen, right? For the screen to screen, yes.
Siva is starring that's it.
This like
Yes.
show thing.
Yes.
Click it.
And the lag is still there.
Lag better or worse?
No, right now this is not moving either. No, it seems to be fine.
Okay. Okay, anyway, let's not worry about the animations, at least they have slides. I think we'll live with this, I guess. So the model we're going to look at today is one of the simplest queuing systems. It's called an MMN queue. There are n servers, and then arrivals happen along according to a Poisson process, which means the inter-arrival time is IID exponential. And the service times for, so the jobs are queued up if all the servers are busy. Once one of the server becomes empty, the job starts service at that server. And the amount of service that is needed is an exponential random variable with service rate, which is mu. In the stock, we'll take mu equal to 1. So it's called MM because M stands for memoryless. Exponential is a memoryless random variable. Since inter-arrival and service times are both memoryless, this is called a MM. N, the N refers to the number of servers. Good. So two special cases of MMNQ
So
are,
we
yes.
can also do this. If you say next, I can press next.
I wanted to skip a slide basically. Otherwise, I have a clicker. Yeah. Two special cases of MMNQ are when n equal to 1 and n equal to infinity. So when n equal to infinity, that's called an MM infinity queue. And what that means is that there's no wait at all. You have infinite servers. Every time there's a job, there's a server that will be assigned to it. So there's no queue at all. And in MM1 there is just a single server, and jobs queue up when the server is busy. Also, one of the most basic things we need to know about a MMN queue is it's stable if lambda is less than n times mu. Arrival rate should be less than the capacity. So these two queues are very well understood. And what we are going to do is we're going to look at the MMNQ in two asymptotic regimes. So I mentioned in my goal that I want finite everything, I don't like asymptotics and so on. I am going to show a theorem with finite everything, but then we want to understand if what the theorem is saying makes sense, how tight the results are. And to do that, we want to look at various asymptotic regimes and see what the behavior is in those regimes, because these regimes are well understood, and that gives us a feel of how tight our results are. So it's useful to have these asymptotic regimes. The way I like to think about this is in terms of that story of the elephant and the blind man. So there's an elephant and the blind man who go to get to know this elephant, and then one touches the trunk, another touches the tail, another touches the tummy, and so on, and each one thinks an elephant is a very different object. I think the asymptotic regimes are all like this. Each asymptotic regime is giving a view of the elephant, just one part of the elephant. And then when we get finite time bounds, usually the finite time bounds are supposed to be kind of giving a much more bigger picture. And then I want to see how from the same finite time bounds, we look at, if we take it to one regime, we reproduce known asymptotic results and so on. So that's a high level spirit of where we are going. And in that spirit, I want to point out two regimes. One is called the heavy traffic regime. So I said lambda must be less than n mu for stability. And if lambda approaches n mu, I'm basically pushing this queuing system to the verge of instability. But the stability means positive recurrence for me, for those of you who are familiar with Markov chains. So I'm pushing it to the verge of instability. So which means the queue length should start blowing up. As lambda approaches n mu, the queue will go to infinity. And I want to understand the way it goes to infinity and so on. That is the heavy traffic limit. And here I let n goes to infinity, m is fixed, mu is fixed, and n goes to infinity. Here n is fixed, sorry, lambda is also fixed here. So here lambda is fixed and n goes to infinity, here n is fixed and lambda goes to n. And this is usually called the mean field limit. And in this limit, the behavior one should expect it to be similar to the MM infinity queue. And what I'm going to do next is I'm going to look at an entire spectrum of regimes between these two escapes. So here I said lambda is fixed and n is going to infinity. Here is the other way around. And what I'm going to do now is I'll take lambda to be something like this. So remember, mu is equal to 1. So maximum value of lambda is n, and I'm allowing a slack in my lambda. And then the slack depends on n itself. So think of alpha as a constant parameter for now. And if alpha is like a constant, then it's as if imagine that there is another constant sitting in front of this. If alpha is 0, let's say, then if there is a half here, then lambda is like n over 2. So that is like fixed load that corresponds to this regime. And if alpha is like infinity, then it's almost like this is kind of like a constant, and that corresponds to the heavy traffic. And then in between, we have an entire spectrum of regimes with mean field on one end and heavy traffic on the other end. So this is the spectrum of regimes, and alpha equal to 0 corresponds to the mean field, and alpha equal to infinity corresponds to the heavy traffic. And we want to understand the behavior in this entire spectrum of regimes. And what is known, especially from the work on steady state behavior, is that there's a phase transition for this queuing system at alpha equal to half. And this alpha equal to half is called Halfin-Whitt regime. Halfin and Whitt studied this in 1981. They did not look at all possible regimes. They looked at this regime because that is the most interesting, because that's where there's a transition from this MM infinity kind of behavior to MM1 kind of behavior. MM infinity behavior means that in steady state, you don't wait at all. MM1 means that especially in heavy traffic. So these are called mini server heavy traffic. Mini server because this n is going to infinity. Heavy traffic because the slack is essentially going to 0. And after this transition, there will always be a wait. The jobs must wait. Okay, good. So this is just a in the next slide, I'm just going to present.
The noise because there are n of them, and so the noise of the order root n.
Exactly, that is the reason. Yes. So what happens is, let's say you have n servers and your load is n over 2, then the number of busy servers should be n plus square root of n. So there is a fluctuation, but you have n idle capacity, so the fluctuation doesn't matter. But when your idle capacity is also order square root of n, then the queuing effect kicks in. Yes. Good. So, like I said, the alpha equal to half was studied by Halfin-Whitt in 1981. And then since then, many other authors, including some of our own work, has been looking at these other regimes. Not all of these papers are focusing on the MMNQ. Some of these are on a different system, but nevertheless, I wanted to just show it here, just because all these regimes are studied in this set of papers. This 1981, they did Halfin-Whitt, and then in the last 10 years or so, there's been a lot of interest in characterizing this entire spectrum of regimes. But all of this is steady state behavior, and we are interested in transient behavior. So in terms of transience also, people have studied. So the expectation is that if the steady state story continues in transient, then whatever the mixing of MM1Q is, we should expect that behavior above half. And whatever the mixing of MM infinity is, we should expect that behavior below half. This is a natural thing to expect. And indeed, the result is going to be of that form. That's what I'm going to state in a couple of slides. But in the literature, people have looked at various regimes. And the entire spectrum was not completely studied. Different authors have looked at different parts at different points of time. So firstly, MM infinity Q, by the way, it's useful to know that MM infinity Q has a stationary distribution that's Poisson. MM1Q has a stationary distribution that's geometric. And then we said that we'll look at this in the heavy traffic regime. In heavy traffic regime, if you do appropriate scaling, this geometric goes to an exponential. So it's as if you have a Poisson here and you have an exponential here. And for MM1 and MM infinity, it's not very hard, and it was done almost 20 years ago. And this is a beautiful paper that talks about anytime there's a phase transition, you need one set of tools below the transition, possibly another set of tools above the transition, but usually at the transition is the hardest to study. This is a beautiful paper that does very, very, very precise characterization at the transition. In our result at the transition, we have very poor characterization. So this nicely complements our work. And then this is a paper that uses something called the log norm approach, and it does only part of the regime that is above half a bit. Okay, good. I wanted to just quickly show the rates in this regime. So in this regime, for MM infinity Q, the mixing is of the form e power minus t, which means the mixing rate is actually 1. It's not even big of 1, it's literally the number 1. So the mixing rate is 1 for MM infinity Q. And for MM1Q, it is the square root mu minus square root lambda whole square. Lambda is the arrival rate, mu is the service rate. I said I'll take mu equal to 1 mostly in this talk. And if you kind of expand this out, then it is of the order epsilon square. So usually lambda is the arrival rate, 1 is the service rate. The gap between them, I'm going to call that epsilon. And because that is a heavy traffic parameter, I said lambda approaches 1, so epsilon is supposed to be small. And so basically, if you expand this out, this is of the order epsilon square t. What that means is that the mixing time is of the order 1 over epsilon square. So in heavy traffic, epsilon is going to 0. So the amount of time it takes to mix is very large.
So these are non-reversible Markov chains.
These are all reversible Markov chains, actually. So that we're going to exploit all of that in our analysis. I mean, a major open problem future direction that we are working on is to develop techniques that work for non-reversible Markov chains. So actually, these are not just reversible; these are all birthday chains. I believe that our techniques need reversibility, but they don't need birth depth structure. But this approach, this spectral method approach, works only for birthday chains. And when you go from MM1 to MMN in this regime, so I said mu equal to 1 and you have n servers, so this is the total capacity. So it becomes basically this expression, which is the natural generalization of this. So that's what I meant when I said that we should expect similar behavior as MM1. And then here we should expect something like e power minus t. And in this regime, this expression, this epsilon square actually becomes 1. That's why in this regime, you should get e power minus constant times t. And what they show in this paper is that there is actually a, if I put this pre-exponent constant of b here, earlier when I showed, I said n minus n power 1 minus alpha, the constant was not at all important. But at the phase transition, this pre-exponent constant becomes very, very important. And what this paper showed is that there is some b star. Below that, it's like e power minus t. Above that, it is the c power minus b square over 4. That's what I meant when I said that they have very, very, very precise characterization at the transition. Okay. Our goal is to get a result that has the right rate, modulo constants, universal constants in this entire regime. And in the next slide, I'm going to state our result. So what we do is this nu is the stationary distribution. Pi is the distribution at time t. N subscript n for a system with n servers. Like I said, I want everything to be finite. I don't want anything to go to infinity. And we are bounding the chi-square distance between the PMF at time t and the stationary distribution. And then we show that that is less than or equal to something times the initial chi-square distribution. And this something decays as e power minus t. And whatever is in that box, that is the rate. That is the mixing rate. Okay, so this is the result. Once, I think I should just kill all my animations. Okay, so this is mm infinity, e power minus t, same as before. mm1, e power whatever this epsilon square t kind of thing. Again, same as before. And this reproduces the result that I showed in the previous slide using log norm, but we reproved it using our approach. The result is the same, so there's no new contribution here. And there was a gap here between half and 1 for alpha between half and 1. And here what we show is that we show essentially the same thing, but we are off by some constant for finite n. But in the limit, this constant goes to 1. Which means that at least asymptotically we're getting the correct. Okay, and here one should expect, there was no result here before, one should expect e power minus t. What we end up getting is e power minus a constant times t. And in the limit, we expect the constant to be 1, but we don't know how to show it right now. What we have is, again, similar to the Cn, we have some constant that depends on n. If n goes to infinity, our constant is 1 over 25. Which means we are off by a factor of 25, basically. That is the universal constant we are off by. Trying to getting the right exact constant of 1 here is still open. So since I said that I wanted exact constant 1, so my student who I tried a lot, he couldn't. So he looked at yet another regime where I said until now that alpha is a constant, but when it's a constant, it's supposed to be between 0 and infinity. Open interval 0 and infinity. So here he is kind of pretending alpha equal to 0. So he's making alpha a function of n and letting it is 0. Essentially what's happening is lambda is the total arrival rate, n is the capacity. So in this regime, lambda over n is actually going to 0. As your system becomes bigger and bigger, if the load, lambda over n is kind of like the load, the amount of arrival rate per server, if that goes to a constant, if that goes to a constant, it's kind of like this regime in some sense. Here, the load is actually going to 0. It is like extremely light traffic. The queue is almost, it's not even being used basically. So in that regime, we actually get the right rate of 1. Again, we get some constant here that depends on n. In the limit, this matches 1. Okay, so I know these regimes can be quite confusing if this is the first time you're seeing them. I think the main takeaway is that we have this way of defining these regimes where on one end you have mm infinity q, on the other end we have mm1 q, and then the steady state behavior is well understood and people know that there's a transition at alpha equal to half. And we are essentially saying that when you look at mixing behavior, the same story carries over. Below the transition, the behavior is like mm infinity. Above the transition, it's like mm1. And modulo, so we prove all of this. Modulo, the only missing piece in our story is that the constants are slightly off. Off by universal constants, not problem dependent parameters. Yes.
Yes. So before you go to the, the proof of this, so there is no control here, right?
There's no control here. That's a very good question.
What happens to, I mean, let's say the Maxwell control when you have.
Good. So that's exactly what we're trying to do now. We don't have any results there. So when we started this project, I wanted to look at one of the simplest system that has max weight control is something called the load balancing system. What is a load balancing system? You have n servers, again, exactly like here, but then each server has a separate queue. And then when customers come, they have to decide which queue to join. They can't change their mind later. So this is called a supermarket system. So it's like a supermarket, especially in US, they have like so many queues, and then you have to go and join one queue, you can't change later. And the most natural thing to do is join the shortest queue. There are other algorithms people have developed and so on, power of two choices and so on, but max weight here reduces to join the shortest queue. So let's say you have joined the shortest queue, and then we wanted to get the mixing behavior of that. Actually, I started thinking about this problem almost 5 years ago or so. I had a master's student to whom I gave this project, and then all he could do was he could get a result when you have two servers, and the rate was not e power minus t; it was kind of like 1 over t. And then the thing in front of t, which was supposed to be epsilon square, he couldn't get epsilon square; he got epsilon cube. So it's like bad in all ways, and all of this only for n equal to 2. So at the time, I didn't even let him publish it. I said, this is like pretty much a useless result. And then when I started working with Huang, I gave him this question. And then he spent a lot of time. And then I was convinced that this is a very, very hard problem. So I called up the master's student who graduated. And I said, I think it's not too bad a result. We should probably publish it somewhere, second-tier journal and so on. So it's under review right now. So what we decided with Huang is, let's actually take a step back. Let's start with a simpler system, MMN system. Like you pointed out, there is no control. And even the underlying geometry of the system is much simpler. There's only one queue. In the load balancing system, there are n queues. So you're living in n-dimensional space, and you have to deal with that. So first we wrote this paper focusing on MMN. And now Huang is thinking about the more general thing. But the question is, are these tools naturally generalizable to the JSQ, join the shortest queue system? Unfortunately, no. Maybe we can adopt at least some of the techniques here, but JSQ system really needs some new ideas to make it work. That's, I think, like I said earlier, I got into this space. I mean, this is pretty much my first work on mixing. So I think this is going to serve as a stepping stone. I think by the time Huang finishes his PhD, we'll probably have more results. Any other questions? Good. I think that's all I wanted to say on this slide. I'll just move on to the next slides. So I wanted to say something very briefly about the notion of distance that we use. We use this chi-square distance, and the reason we use this is primarily because we end up using Poincare inequality, and when you use Poincare inequality, chi-square distance shows up naturally. But chi-square distance belongs to a family of f divergences. If you have a function f that has some properties, then you can define f divergence between two distributions using some formula that looks like this. If the function is x log x, then we get KL divergence. If the function is the absolute value x minus 1, you'll get TV divergence. And if the function is x minus 1 whole square, like quadratic basically, then you get chi-square divergence. And moreover, it's well known that if you look at any f divergence, locally it's kind of like chi-square. It's basically like doing some kind of Taylor series for this divergence, and then if you truncate at the first term, then you end up with chi-square. Okay, fine, whatever. What do I care? One nice thing about chi-square divergence is that I'm not going to go through the calculations, but the punchline is that I can get a bound on the distance between the means in terms of the chi-square. And there's nothing sacred about the mean. I can do the same thing for moments. I can do the same thing for MGF of this guy versus this guy. The distance between the MGFs of these guys can be bounded by the chi-square divergence multiplied by something else that we need to have a handle. And using this connection of chi-square divergence, we take the previous result, Our previous result was basically that the chi-square distance between the PMF and the stationary decays exponentially. So once we plug that here, then we'll get an exponential rate of convergence on the distance between the means and moments and MGFs. That's what I'm going to show in the next slide. So this table is the same table we saw before. Nothing has changed. Essentially, all I'm saying now is that I can look at the mean, because remember when I started off, I said that in practice we care about mean at finite time. So if you know the stationary mean, then we can say that my finite time mean is away from the stationary mean, by this exponentially decaying term. And the only difference compared to the previous theorem is that this additional big O term, which is basically the expectation. Remember in the previous slide I had I'm so scared of going back. I had this additional expectation, so we have to essentially calculate this expectation, and that gives an additional term on the right. That's pretty much it. We do the same thing for tail bounds also, using the Chernoff trick. Chernoff trick is simply that to get tail bounds, you have to use the Markov inequality. But if you use Markov inequality on the mean, if you use Markov inequality directly, it's very loose. So you use Markov inequality on the exponential function, then you get a nice exponentially decaying tail. But to use this, you need to get a handle on the MGF of the Q length. And our chi-square distance enables us to do that. And then once we do that, we get a tail bound that kind of looks like this. By the way, these regimes above half, we call them Super-Halfin-Whitt regimes. And the ones below, we call them Sub-Halfin-Whitt regime. So in both the Super and Sub-Halfin-Whitt regime, we basically plug and play the chi-square distance, and then we get a handle on the MGF. So based on prior work from my group, we have a handle on the MGF, stationary MGF. And then once we put them together, we get tail bounds that look like this. So the tail is supposed to decay kind of like exponentially, because I said that MM infinity stationary distribution is Poisson, and MM1 stationary distribution is geometric, which can be approximated by exponential. So Poisson also has more or less exponential like tail. So these are supposed to be pure exponential, but anytime you use Markov inequality, then you end up with a pre-exponent term. That's an unfortunate thing about Markov inequality. So the square root of x is not supposed to be there. Any questions?
The square root of x is coming from it's probably coming from the fact that it's approximately like this, going from the stationary to the.
Okay, let's say you have, forget about all of this. Let's say I give you an exponential distribution. When I give you exponential, you know it's PDF, CDF, MGF, you know everything. Let's say I don't allow you to, let's say I want you to take the MGF and apply Markov inequality and optimize over your choice of theta. Then you will end up with some pre-exponential. That is why we have this. Yes. Yes. But if you actually do the inverse Laplace transform, then you'll get the exact answer. But Markov inequality is not good. Cool. Any questions? Okay. So if not, oh wow. I'll use the next 20 minutes to talk about the proof technique. So I forgot to say this in my first slide when I talked about overview of my work in many areas. One common theme that has been that underlies all my work in stochastic approximation, queuing, matching, everything is use of Lyapunov approach. Constructing right Lyapunov functions and then using Lyapunov arguments. Lyapunov functions are also called potential functions. So in this context, in the context of mixing, a Lyapunov argument looks something like this. So continuous time Markov chains have something called the generator. If you don't know what the generator is, think of a DTMC, a discrete time Markov chain. It has a transition probability matrix P, and P minus I. P is stochastic matrix, rho sum equal to 1. Minus I will make rho sum equal to 0 with diagonals being negative. P minus I is the analog of the generator. Essentially what I'm doing is I'm looking at the change in my Markov chain over one time step. I basically means wherever I start, identity, and then P looks at one step, next step, and then the change, P minus I looks at the change. So the generator is the natural generalization of this notion. So in continuous time Markov chain, time is continuous. So instead of one step, you should think of it as like time derivative. So this generator is the right way of doing time derivative for Markov chains. So essentially, the Lyapunov approach is that if I look at the right generalization of time derivative, that is a generator applied to a function, this V is the magical function, the Lyapunov function, and suppose I get an inequality like this, then intuitively speaking, this inequality is essentially saying it is kind of like this. Forget about this B for a moment. If I have a ODE, V dot less than or equal to minus gamma V, then we know how to solve it. It is just e power minus gamma t. I don't know anything about ODEs. This is the only ODE I know how to solve. If there's the equality, it is e power minus gamma t. Groundwall's lemma says that the same result holds true with inequality in the inequality case. Now, what this is saying is that my Markov chain also should have the same property. If I apply the generator to a function V, suppose I get minus gamma V, but I'm giving you slight slack. I'm saying that it should be minus gamma V everywhere except one state, which I'm calling x star. So then suppose you can prove this, then similar to solving this ODE, one can immediately get a result that looks like this, that the chi-square distance decays exponentially fast with the rate of convergence being this gamma. Okay, and let's see this in action. Suppose you have an MM1 queue, which is one of the simplest queues like I mentioned earlier. So arrivals are coming with rate lambda, service is happening with rate 1, and there is randomness everywhere, but if you kind of not look at the randomness, if you just think of this as fluid coming in, the rate of change of the queue length is like minus epsilon. Rate of change of the queue length is plus lambda minus 1. 1 minus lambda is defined as epsilon, so q dot is minus epsilon. But remember, the ODE I wanted is v dot is minus v. This is not of the form q dot. If I had q dot equal to minus q, that would have been in the form of the ODE, in the ODE form that I wanted. Unfortunately, this is not. So what I do is, instead of working with q, I work with this function v of q equal to some exponential of q. Then when you apply v dot for this and then use the chain rule, you'll end up with v dot being approximately minus something times gamma or something times v. Okay, and so this is now looking like what I want it to look like. Therefore, I'll work with Lyapunov functions of this form. So this is how one comes up with Lyapunov functions. So coming up with Lyapunov functions is a little bit of an art. And the good thing is that you can wave your hands, ODE. If you ask me what is the connection between this ODE and this Markov chain, I don't have to explain that to you because this is all hand-wavy. This is just for intuition. I'm using this as an intuition to construct my Lyapunov function. And the proof is basically working with this Lyapunov function and then showing that it satisfies an inequality that looks like this. If I apply generator to this Lyapunov function, you have to choose that. You have to make the right choice of theta to come up with the right rate. I'm hiding all of those details under the carpet. Then you'll get that this generator applied to V is less than or equal to minus a constant times V plus turns out you can never show just this. It's pretty much impossible in Markov chains to be able to show just this without any additive constant. And here I have this additive constant only in state 0. Like I said before in the previous slide, in the Markov chain setting, we allow this additive constant, and then this implies basically mixing at this rate, and this was the rate that we had before for MM1Q. Any questions on this?
This you require every right, to get the mixing.
Sorry?
To get mixing time, what you require is for every.
No. No, just one V.
Which V?
This is the V I'm using.
Then I don't understand. I mean, like.
So the point of this is not Poincare inequality. Forget about this line. Poincare inequality needs it for all functions. The point of Lyapunov approach is that if I find a single V, I think the only other property this V should satisfy is that it is lower bounded by 1, I believe.
No, but the thing is, in the end, you want to get to L2 or something, right? So that requires. I mean,
there is a lemma. We have it in the paper that says that if you have something like this, I can show a Poincare. If you have something like this and the V is lower bounded by 1, I can get a Poincare inequality with this, with the inverse of this as a Poincare.
For one V, but that V could be 0.
Correct. So it should be lower bounded by 1 and it can't be constant. I think it should go off to infinity. There are some conditions. It should be lower bounded by 1, but it can't just be, wait. No, even if you use a constant, you can't show this, right? If you use constant, LV will be 0. Then you can't show
And
this.
then that's the other side. Apart from the B, it's correct. LB is 0 and the right hand side is just B and so on.
0 less than or equal to okay. But it has to be lower bounded by 1. So it has to be positive, strictly positive basically. Again, the intuition is something kind of like this. So in ODE world, if I want to show behavior of this ODE,
No, this I understand, but so the thing is that inequality itself, right? Usually, yeah. So I mean, the thing is that pointer inequality will be equal to the form that LV is less than minus C times V for every V. I mean, that's what the pointer
correct.
Showing that the pointer inequality holds, but not for every V, but for
But only for one V, correct.
But from there, you are able to get a mixing time out, which is more or less equivalent.
In fact, actually, we get a Poincare inequality. That is the in-between step. Starting from this Lyapunov drift, we proved Poincare inequality, and then that implies mixing.
Yes.
The fact that this indicator is at 0, does it have anything to do with mu1?
Mu equal to 1? No. That just have to do. So basically, what is a queue? A queue has arrival and departure. It seems like a very linear operation. There is just a single nonlinearity that corresponds to when the queue is empty. So, and this 0 basically corresponds to that nonlinearity in the definition of queue.
No, I mean the fact that this inequality holds with the indicator at 0 rather than some other state, does that filter into some state?
No, it can be anywhere. It can be anywhere. That is not. Okay, cool. So this is MM1Q, and MM1 result was known for a very long time, and that result was not proved this way. But anyway, we can do this proof. But the main issue is this singleton. MM1 is a very simple system, and so one is able to find a V that satisfies this, where this set, this bad set, let me call this a bad set, this bad set is a singleton. But most of the time, when you try to use Lyapunov approach, you end up with a Lyapunov function, and you may be able to show an inequality that looks like this, where this bad set is not a singleton, but it's a finite set. And dealing with this finite set, finite or small set, dealing with this jump from singleton to a finite set has been a main problem in a lot of work on Markov chain, not just Markov chain mixing, on something called geometric ergodicity. There's this famous book on by Main and Tweedy on Markov chains, especially in finite-state Markov chains. And they talk about something called geometric ergodicity, which essentially means that you have geometric mixing, but they don't worry about what the mixing rate is. All they want to show is that there exists some rate under which you'll get this geometric thing. They've developed a lot of tools to handle this non-singleton nature of the set, but those tools don't give the right rate. The results I showed, our rates are very, very precise, modulo just that factor of 25 or whatever. But for example, the dependence of our rate on the problem parameters like epsilon square and so on was very precise. So that's impossible to get using the tools from Main and Tweedy. So what we do is that we first establish an inequality like this, and then we focus on the finite set. So once we focus on the finite set, one can essentially think of this as a finite state Markov chain. And then for this finite state Markov chains have a lot of tools to establish their mixing. And one of them is Poincare inequality, which looks something like this. Poincare inequality is essentially a spectral argument. So we all know that, so if you think of it DTMC again, there's a transition probability matrix P. It's a stochastic matrix. It has an eigenvalue at 1. And then the other eigenvalues are inside the unit circle. And then the gap between the unit circle and the second largest eigenvalue that determines the mixing rate. And Poincare inequality essentially captures this in the form of an inequality. And the constant here corresponds to the spectral gap. And in a finite state Markov chain, if you establish such an inequality, and as Piyush pointed out, this should be established for all functions f. Then one has mixing for the finite state Markov chain. And what we are doing is we are combining these two things. What we are saying is that take your big infinite state Markov chain, first establish something like this, then focus on this finite set. And then for this finite set, if you can show a local Poincare inequality that looks like this, then we have a lemma, we proved a lemma, which says that for the big entire Markov chain, we have mixing, we prove that there is a Poincare inequality for the entire Markov chain, and the corresponding Poincare constant is this. So what I'm saying is that for the finite set, if you show an inequality like this in addition to Lyapunov inequality, then for the entire Markov chain, I establish an inequality of the same form with this different constant sitting here, and that immediately implies mixing rate with this is the Poincare inequality for the big chain, and that immediately implies a mixing of chi-square with rate that is inverse of this Poincare constant. So this lemma itself is not new. We actually learned of this lemma in the literature. I think I have references here. There are various forms of this lemma in the literature. We kind of generalized it a little more so that it is suitable for our application. We did some weighted local Poincare inequality and so on. And this is good because we get at least something, but this need not be precise in general, and this is part of the reason why we are off by that constant of 25. Any questions?
So this step 2 is restricted to K?
Yes, it is actually. That's why, nu is a stationary distribution. It's a distribution, so it has measure 1. But here I'm looking at nu of K because I'm only restricting to K.
That inner product is also new.
Yes. Cool.
And the edges going out are set to 0 or?
I think if you make f equal to 0 outside, it doesn't really matter, right? Yeah, exactly. Because this is algebraic inequality, you don't have to worry about it. Good. So what I want to do, I don't have much time. I'll focus on just one of the regimes, and I'll tell you what we do in this regime in both of the steps, and then I'll stop. Okay. So this was the high-level proof framework. So we just have to do these two. Once we do these two, this comes from our stitching lemma, and then we have the result. So let's start with the first step. So I'm looking at the setting where alpha is greater than half. So we know that we know from the theorem that the behavior is like MM1Q. Even before the theorem was proved, intuitively we knew that. So we know that we have to use a Lyapunov function that comes from MM1Q. So what we do is we look at an exponential Lyapunov function. So someone asked if the chain was reversible. The chain is indeed reversible. It's actually birthday chain. The arrows going up are all lambdas. The arrows going down, the rate is basically, here it is 1, here it is 2, 3, 4, 5, up to n. After that, it is just n. So the downward drift is lambda is this much, minimum of q and n. Upward drift is lambda. Okay, and the point is that lambda is somewhere in the middle. If your q length is very small, there is a strong upward drift. If it is very large, there is a strong downward drift. But if you are somewhere in the middle, the drift is not very strong. And this is the source of our difficulties with the non-singleton or all of that. So I'll continue with the intuition from before. For MM1Q, if you're far away, if your q length is somewhere here, then the drift is kind of like minus epsilon. So I'll use an exponential Lyapunov function, potential function, and I'll use an exponential potential function. But to make it work, we just have to do it slightly differently. Above n, we use a different. So basically, this is an exponential function. If your q length is above n, we use one particular parameter θ1. If it is on the left-hand side, we use a different parameter. That's it. That's the only twist here. Modulo that, it is just the usual exponential. So one interpretation of this is on this side, when the q length is above n, remember you have n servers. Q length is the total number of people in the system. If you have more than n customers, that means that some are waiting. And q minus n is the number of waiting customers. And when your q length is less than n, n minus q is the number of waiting servers, idle servers. So the Lyapunov function is essentially of this form, e power some θ1 times number of waiting customers and θ2 times number of waiting servers. Okay. If θ1 and θ2 were equal, this would have just been an exponential e power q. But for whatever reason, when we played around, I think these Lyapunov functions, it's like I said, it's like an art. So you come up with something and sometimes it works perfectly. Sometimes you have to do some carpentry. Then once we do this, we essentially get this LV less than or equal to, this is same as what we had in MM1Q times V plus this indicator stuff. But unfortunately, this indicator, this is a finite set around the mean, around the lambda. It's not singleton. That is the main challenge. So now what we're going to do is, so this finishes step 1. And then now what we'll do next is go to step 2. When the slide moves. So step 1 is complete, and this is that indicator of the finite set. Now we'll go to step 2. So for step 2, we have to focus on this finite set and worry about the local mixing. So if you think of this, so this is a birth-death chain. Think of it as a finite state birth-death chain. I mean, this is not 3 states; it is a bunch of states. But the arrival, all the upward rates are lambdas. Downward rates are not constant; they depend on the state of the queue. But turns out that this set is not too large, which means the variability in this downward rates is not too much. So suppose I give you a birth-death chain with constant up rates and constant down rates. Stationary distribution will be uniform. And then how would one show its mixing? There is something called the canonical path method for showing mixing of finite state Markov chains. It's a way to basically count the number of paths between every pair of states and then give some weight to these paths based on the stationary probabilities. And then when you do this calculation carefully, then that gives a mixing bound, mixing rate. This is similar in spirit to Cheeger and things like that. So we adopt, and it is known that this canonical path method works when the chain is very close to being uniform. All the rates are constant. And indeed, in our case, that is the case. They're not exactly constant, but they're close to constant. So canonical path method can be used, applied for any chain. But the rate it gives might be very bad. It is known to be good when the chain is close to uniform. And so we use the canonical path method. And the size of our finite set is of this much, n power 1 minus alpha. Alpha is my parameter. And usually canonical path method gives a mixing time. If it is a DTMC, it gives a mixing time that's order d squared. And but we have a CTMC. At each time, the number of transitions are approximately order n. Think of the arrivals. Lambda is order n. So which means in terms of time, it should be d squared over n. So indeed, that is exactly the local Poincare constant we get corresponds to this d squared over n. So if I use the size of d that I showed in the previous slide, n power 1 minus alpha, and substitute, I get a mixing time of this, and this is essentially what my local Poincare is telling me. This also is why I need alpha greater than half, otherwise that guy is not going to 0. So now I know this, I put them together, plug it into this formula, and then so this is the Poincare constant, CL, and then once I put it into this and calculate the CP, I get the theorem that I mentioned here. The CL is some constant for every n. As n goes to infinity, it goes to 0. And then when this goes to 0, I end up with just this part. That's the reason I had a result that looked like this. This some constant times this thing, where the constant goes to 1 as n goes to infinity. Okay. I think I'll stop here.
So what is the reason or what's the barrier to getting Gamarnik et al.'s result by these methods?
So we do that. So basically what I showed you only one of the regimes, right? We also do the other regime. So this is the regime immediately above Halfin-Whitt. Then there is the one just below Halfin-Whitt. I think at the transition, you can ask what happens if you use this method, what happens if you use this method. In one of the methods, it utterly fails. We don't even get mixing. But in the other direction, we actually do get some result. But the constants are terrible. We get some 50,000 and things like that. So, but if you look at the Gamarnik et al. Result, they have a very, very, very precise bound. They not only look at this square root of n, they worry about the constant in front of the square root of n in lambda, the b. And then they say that if b is below something, it has this behavior. If it is above something, it has this other behavior. So our methods are just not precise enough to do.
So you have a very detailed understanding of what happens at k, you would not get something.
I'm not 100% sure because so what you're saying is okay. What are our sources of looseness? One source of looseness is the local Poincare maybe is not precise enough. The other source of looseness is that the stitching might be introducing something that is bad. I think what is happening in this, I think in some sense the Super-Halfin-Whitt is easy because the mixing rate is poor. It is 1 over, the mixing time is 1 over epsilon square. It's taking so long to mix then whatever analysis I'm doing, if I introduce some small error in the stitching lemma, that's washed away by this 1 over epsilon square. So that's why it is relatively easy here. When we go to sub-Halfin-Whitt, the mixing happens super fast. It is order constant. So whatever stitching we are doing, that error is not washed away. That's the reason we have that off by 25. And then at the phase transition, we have to have even more precise understanding. And since we don't have it, we have this ridiculous constants.
The canonical path is usually. I have surprised actually hit the phase manager. Usually,
I know. I think that works mostly because in this set it is almost uniform. That's the reason. Correct. Yeah.
I guess the path is the only place where it gives the right result.
Correct. Exactly. Yeah. But I think maybe one takeaway I wanted to show in this thing, maybe I'll just show that slide, is that if we look at finite state Markov chains, there are many methods. Okay, let it come. There are many methods for finite state Markov chains, Chigger, conductance, and all this new work by Nima Anari and his co-authors on spectral independence and so on. And then for countable state chains, there are not many methods. Spectral method is essentially directly showing Poincare inequality. Poincare inequality is just an algebraic inequality. You can forget about Markov chains and do whatever algebra and then show that inequality. For MM infinity, it is possible to do this. But for MMN, it's almost impossible. Log norm I mentioned before, and coupling or hitting times, somehow getting a handle on hitting times using coupling arguments. So these have been the tools that people were using all along. So I think our contribution is essentially to say that using Lyapunov arguments due to this finite set and stitching theorem, we can reduce the problem of studying countable state Markov chains to finite state Markov chains. So you could now possibly use all these tools to develop that local Poincare inequality and then use that to study countable.
This kind of thing is also used in finite Markov chains. Like there are results which can be seen as that from an arbitrary state, weird things happen. So you wait for a while.
I see.
So often people will call this.
Warm start.
Yeah, warm start, but also so it's not exactly warm start. You start the cold thing, but you just wait for a while before So chain is not mixed, but it has some nice properties now. At this point, some of these methods might start to. So there
I see. Maybe the difference is that there you are doing this over time in some sense. Here I'm not even thinking of time. All I'm thinking is that I construct a Lyapunov function, then I reduce the problem.
So there it's usually like you say that, so it's often like you say that after a little while, your chain will be would have somewhat warmed up.
I see.
And at that point, one of these
things will apply. I see. Cool. Any other questions? Thanks. Oh, yeah.